Alright, we have a lot to cover, so I'm going to be going decently quick. My name is Brian Brown. I did the Rockine Recycle report. Just a brief summary. Patrick covered a lot of it. The main objective is to really just understand the Rockine cycle, how to analyze this, since it's just a huge component of our current power generation. The theory, you're going to pump water into a boiler. The boiler's going to bring it to a high pressure steam. The steam's going to get throttled out into a turbine. The turbine's going to turn a generator. The generator's going to generate electricity, and then it's going to leave this, the steam's going to leave the turbine and go into a condenser, in which it will be either reboiled or, in our case, it's going to get let off into the atmosphere through a condenser tower. This is the apparatus, much like the one that he has on his. But here's the actual picture of it. You can see we have the condensing tower, which is a little bit different than what most diagrams show it to be. And then here's kind of a little software where you can monitor different things. This is the raw data. It's said to specify a time within the steady state to kind of like analyze. So I chose 400 seconds due to, oh, awesome.
Just try to pull it up again.
I hope that doesn't count.
Time's a waste of it.
Hopefully this works. So it's said to pick a time within the steady state that to just analyze and use kind of as a point of reference. You start logging data at the steady states, so your start and finish points are basically where you stop logging, stop logging. This was the fuel flow rate. Here's the boiler pressure and temperature. You can kind of see it starts to climb, and the pressure kind of stays constant. It moved around a little bit whenever we're messing with it, trying to get it really kind of dialed in. But the reason I picked 400 seconds is here. You can kind of see, like, this is where it kind of starts to wig out and do some weird stuff, so I figured this is probably a really good kind of span of data to analyze. This is a turbine inlet and outlet pressure and temperature. Kind of does some crazy stuff there at the end.
Try enable editing, because it said it was having a problem with protected view or something.
Sorry guys. Technology is not my friend today. This is the electricity. You have amps and voltage, which you can read on your kind of dashboard. It kind of like fluctuated a little bit, and then there at the end it kind of spiked. Here's the RPN. This is really something that I kind of want to point out. You can see it kind of closely follows the relationship between the amps and the voltage. You can kind of see the shape is pretty similar. So there's like a direct relationship there. I want to point that out. This was the data at 400 seconds that I chose to analyze. You have your atmospheric pressure, your initial volume of water that you're going to boil, your fuel flow rate, your pressure and temperature of the boiler, your pressure and temperature of the inlets and outlets, and then you have your V condensed. So this is the amount that we got back, and V is the total amount of water that was boiled. So you heat out of the boiler. There's a little bit of confusion here. The pressure drop from the boiler to the turbine was actually quite massive because it's being throttled. This kind of caused a little bit of confusion for me because it being at the state that it's at the boiler, and then leaving it going to the turbine, the states just weren't making any sense. But here are the calculations that I used. I used the inlet and outlet conditions of the boiler, and the the inlet conditions of the turbine for the outlet of the boiler, just to kind of make things line up right. And then there's the mass flow calculation with the heat flow. The work rate and the turbine efficiency, you just use the inlet and outlet states, and then you get a watt for the rate of the work done, and then the efficiency is here. H4S is basically if you look on like the diagram at the beginning, H4S is where the enthalpy kind of like shifts around from the ideal state to the actual state. And so that's kind of where you take that, that's at the saturation line. For the condenser, you have your outlet of the turbine going into the condensing tower. Here you can use the condensed volume versus the boil volume to get an efficiency rate. I use that versus the state stuff because it's kind of confusing, and this is a more accurate result in my opinion. That's the heat rate evaluated at 400 seconds. Here's the mass flow rate that we used in pretty much all the other calculations. It's the condensed amount times the density divided by the time to give us the right units. Here's the table of values for everything. Just interpolation city is basically what that is. It took forever for all that. The thermal efficiency of the whole system, I'm not too sure exactly why it came out the way it did. I think it has to do with the fact that you're not reboiling any of the water, it's all just leaving. So I think that's why. And then we also lose a ton of pressure coming from the boiler. You have about 110 pounds coming from the boiler, and then when it goes into the turbine, it's like 16 pounds. And that's usually not really good. Usually in an ideal setup, you want to just be able to utilize all that pressure. But I think for lab purposes, the pressure was pretty, you don't want 110 pound steam running into a turbine that's this big. Loading the turbine increases the work required to spin the turbine. So basically, and another comment I want to make about this is whenever you go to start up, for people that are doing this lab, you want to load it before you actually start throttling it, because if you don't, you'll blow the bearings out, and that will make them not very happy. So the higher the load, the more energy must be pulled from the boiler. So if it's loaded higher, you're going to need more pressure and steam to generate electricity. In summary, the Rankine cycle is a huge part of modern day power generation. Understanding how to analyze that and all the different components associated with it is important for us as mechanical engineers to be successful in a plant setting. Also, loading a turbine will prevent it from overspeeding in most cases. They also usually have like trip things that will trip if it starts to get too fast, and they'll start to cut off everything. An overspeeding turbine is incredibly scary, by the way. Is there any questions? I am way over my time.